Hi everyone, I'm Christophe Durand. Today I will present the new automated grid code analysis that will be released in ETAP 22. In this presentation, I will first introduce the main grid code requirement, and then I will present an application case about reactive power supply analysis according to PQ and VQ diagrams, dynamic simulations under disturbed conditions, and I will finish with harmonic analysis. Many countries have adopted long-term objectives to move away from fossil fuels and achieve carbon neutrality in 2050 as per the Paris Agreement goals. The process will involve a deep transformation of the economy and radical changes, especially for the electrical power generation. The system operators and energy producers are shaping strategies to achieve this goal. To produce low-carbon electricity, the renewable power plants will play a key role with a very high penetration rate, up to 100% in some areas. The authorities in charge of the system integrity and network operations specified the technical requirements that the renewable power plant have to comply with. These requirements are known as network or grid codes. Grid codes are technical specifications which define the performance of power generation connected to the public distribution and transmission networks. The grid codes are written by the transmission and distribution system operators in order to ensure safe and stable operation. They can be split into different sections. The first section is the planning code. It's aimed at defining the TSO and user interaction in respect of any proposed development on the user system that may impact on the performance of the transmission system. The planning code defines the information required by the TSO for planning, development, and forecast. Then, the connection conditions define the technical, design, and operational standard which must be complied with by any user connecting to the transmission system. I'm going to present some of the connection conditions in the following slides. And the operating conditions provide details for operational procedures such as demand forecast, operational planning, and system services for frequency and voltage controls. On this slide, we have the main topics addressed by the grid codes. They define the normal and disturbed operating condition, and they specify the capabilities and the control modes to be implemented. They also specify the power quality requirements based on flicker and harmonic evaluation. To achieve protection discrimination with the distribution system, the operators specify the maximum fault clearing time and anti-ice landing protection. Those requirements depend on the utility and the country, as each utility defines its own code. In Europe, the European Network of Transmission System Operators for Electricity, known as ENTSO-E, define a common framework for the interconnected transmission system. The voltage at the point of interconnection and also the reference power of the power plant have an impact on the requirement. Usually, small generation units have few constraints, whereas larger ones must comply with much more challenging requirements. The system operators define normal and abnormal conditions. They are classified according to duration and magnitude of both voltage and frequency changes. Within these operating ranges, renewable power plants must stay connected to the grid, and they must produce at least the minimum active power specified by the system operator. This requirement is aimed at preventing renewable power plant disconnection during unstable operation. One of the main ancillary services provided by the renewable power plant is to manage the voltage at the point of interconnection. Grid codes define two types of reactive power capability, P versus Q and V versus Q. The renewable power plant must be able to operate in the complete PQ and VQ diagrams. PQ diagram defines the reactive power capability from no generation to the maximum power, and VQ diagrams ensure that the renewable power plant is able to produce or absorb enough reactive power for the whole voltage operating range. VQ capability must be checked for several active power levels, typically from 10 to 100%. Nowadays, highly demanding power control functions are requested by the system operators. Currently, to meet the most challenging grid codes, large renewable power plants must include a power plant controller. It should be capable of managing both active and reactive power with fast response time for different control modes. The most widely used control mode is the voltage control, so the renewable power plant achieves voltage management at the point of interconnection. The other common reactive power control modes are power factor and reactive power controls. Some system operators also ask for active power control loops. The active power control can be performed centrally from the power plant controller, but the generation units such as inverter and wind turbine generator may embed active power control for under and over frequency conditions. In such a case, the renewable power plants have to manage an active power reserve for under frequency conditions and reduce the generated active power for over frequency conditions. Voltage and frequency read-through are also very important. The renewable power plants must stay connected during disturbed conditions. In addition, distributed energy resources must also contribute to the fast voltage recovery plan by injecting reacting current when the voltage is outside of the normal operating range, for example, plus minus 10%. The injected reactive current may reach 100% of the rated current in some grid codes. The requirement is checked at the generator terminals, and the response time must be very fast, typically 1 power cycle. Now, regarding power quality requirements, generally for low power generation unit, a power quality analysis is not required. But for large-scale generation unit, the system operator allocates additional harmonic content to the renewable power plant. The allowed incremental harmonic voltage distortion level is based on harmonic planning levels, background harmonic distortion, and planning margin. So an harmonic study is required to confirm that the renewable power plant connection to the transmission system doesn't result in an increase in the level of harmonic voltage distortions above the allocated limits. The renewable power plant takes also responsibility for limiting voltage fluctuation caused by the plant operation. Voltage fluctuation must be evaluated for transformer in rush as well as connection and disconnection of the generation units. The last item is the flicker. The grid code or the local applicable standard define the flicker limits at the point of interconnection. Now, regarding protection and coordination, generally the local standard defines the main requirements such as the maximum flickering time. The grid code defines additional protection functions known as anti-islanding protections. These protections are aimed at preventing from incorrect operations such as islanded operation or wrong synchronizations. This anti-islanding protection is composed of residual and phase voltage protection as well as frequency and rock-off protections. The protection schemes and settings for internal electrical fault must not jeopardize fault rise-through performance. That's why the dynamic simulation, like voltage and frequency rise-through, must include all the protection functions to perform a global review. Okay, let's move to the software. I'm going to demonstrate how automated grid code analysis can be performed with ETAP. First, let's take a look at the project that we have here. We have 6 PV boxes, including PV arrays and 3 MVA inverter. This project also have a capacitor bank of 2 MVR and an energy storage system composed of lithium-ion battery and an inverter. A step-up transformer of 30 MVA transfer the power from the collection system to the grid. So for this project, we use the AC PV array element. It includes both the PV panels, the main DC cable, and the inverter. We have an extensive PV panel library, and the inverter editor is composed of AC/DC rating, short circuit current contribution considering voltage dependency, as well as a reactive current control for disturbed operation. For the energy storage system, we can model different technology of batteries. In addition, the battery element includes a battery management system, BMS, to define the criteria for switching from charge to discharge modes. To model a renewable power plant, you can take advantage of our templates that we provide within ETAP. We can create a template for an individual PV box, so I select the elements and click on Add to Template. We provide default templates, and you can create your own template and temp them anywhere in your directory. You can share the template with other users and reuse it for future projects. A template is composed of one element or a group of elements, and the template contains the connectivity between elements as well as the properties. There are several controllers in this project. There are primary controller to transmit set point to the renewable generator and send data to the secondary controllers. The secondary controller element can be used to model the power plant controller and data exchange with the TSO. Thus, we can perform model-driven simulation to validate the algorithm of the power plant controller, for example. The controller element can also be used for automated grid code studies. This feature is included in the grid code analyzer element. In the DLL page of the control editor, we define the parameters such as the type of study, PQ or VQ capability, and the point of interconnection with the grid. In the capability analysis section, you can enable or disable energy storage system and reactive power compensation devices for PQ and VQ capability. The grid code requirement can be modeled with the rulebook. Thus, once the requirement has been entered, you can reuse it for future projects. We can enter PQ, VQ, PV, and PF profile. We can also model grid requirement and PQ diagram in Excel. Reactive power capability of distributed energy resources includes voltage dependency for accurate simulations. I created some scenarios for PQ and VQ capabilities. For each scenario, the grid code analyzer has different parameters. The parameters are saved in the revision with the data manager, and we can run a batch of scenarios with the study wizard. So I'm going to run 6 scenarios for PQ capability with different voltage level at the point of interconnection with or without the capacitor bank. Once the calculation is completed, you can compare the results. For example, without capacitor bank, the renewable power plant doesn't comply the grid requirement in this area, but if the capacitor bank is in operation, then the power plant meets the grid requirements. For the deliverables, you can open the report automatically generated by ETAP, or you can create your own report with Python scripting. Now we can do the same thing for VQ capability. So let's run the study macro with 4 VQ scenarios. Then we get 1 VQ plot per scenario. We see the renewable power plant capability and the grid requirement and identify where reactive power capability is lower than the grid requirements. Now I'm going to present dynamic modeling and simulation. Regarding dynamic modeling, there are 2 methods to create dynamic model for inverters and wind turbine generator with ETAP. We can use the UDM feature for user-defined dynamic model. In the UDM editor, you can create custom control loops or select existing models such as the generic models provided by the WEC for Western Electricity Coordinating Council. This association has developed a series of modularized, standard, and publicly available set of dynamic models. Those generic models are not specific to any particular vendor. They can be parameterized to adequately emulate the dynamic behavior of many vendors' equipment. They provide dynamic model at the individual unit level for renewable generator and the associated controller, and they provide dynamic model at the plant level with the power plant controllers. Specifically for wind turbine generator, there are a series of mechanical side models. So the UDM editor is the first approach for dynamic modeling. We can also use DLL files provided by the vendor. In that case, ETAP provides a black box bridge with a dual DLL approach. One DLL is responsible to collect data from ETAP, initiate and execute vendor DLL, and exchange data between ETAP and vendor DLL. This file is assigned to a controller element in ETAP simulation software to first get associated with primary components such as PV and wind generation elements, and also acquire controller user settings. The user settings are defined in an XML file associated to the DLL at the same location. ETAP also provides templates with all the relevant files to develop vendor DLL. In this example, we implemented the WEC generic dynamic model based on DLL file hosted in the inverter controller. Parameters for PIG controller are available in the controller interface under control settings section to adjust the behavior of the inverters. We can also implement the internal voltage and frequency protection for the renewable generator. In this example, internal protection are implemented under write-through section with pickup and delays. I prepared some scenarios for voltage and frequency write-through. In the study case of the transient stability module, we define the voltage profile in the event page. For this example, the voltage at the point of interconnection will be reduced by 20%. We can also define a voltage ramp. Now I'm going to open the scenario wizard, and I run the scenario with a 20% voltage tag. Once the simulation is completed, we can display the results on the one-line view with this slider, and we can use also the transient stability plots. So I select the power flow for the transformer for the PV box number 1. We see active and reactive power as well as the current. Current and reactive power increase to improve the voltage stability at the point of connection. After 3 seconds, the inverter is automatically disconnected according to the setting of the internal voltage protection. Now I'm going to run a high frequency write-through. As per the study case, the frequency will be increased by 2.7%, 200 milliseconds after the beginning of this simulation. Okay, now I run the scenario. And first, I'm going to plot the frequency and the voltage at the point of interconnection. So we can see the frequency is increased by 2.7%. And now we are going to check dynamic behavior of the PV inverters. After the frequency rise, the active power produced by the inverter decrease down to 2.45 megawatt. So the PV inverter tends to mitigate the frequency rise. We have finished the demonstration of the dynamic modeling and simulation. Now I'm going to present the harmonic module for grid code studies. Harmonic module includes 3 study types. The first type is the harmonic load flow. It calculates voltage and current distortions and compares the results with the permissible values defined in the standard, such as IEEE, IEC, or G55 for UK. We see on this plot the harmonic current distortion in the main transformer and in the PV transformer. The second study type is the frequency scan. It calculates impedance on the buses to detect resonance. On this plot, we see a resonance for the harmonic order 36. This is due to the cable capacitance and the 2 MVR capacitor bank. The last study type is the harmonic grid code. This study type includes automated harmonic analysis for detailed power quality assessment report. It demonstrates that the power plant is designed to comply with the applicable harmonic limits. Individual impedance graphs are used for each harmonic order, and a scatter plot of the harmonic impedance values is plotted. The number of points is defined in the harmonic study case in the grid code tab. This study type also identifies a combined pair of impedance points between transmission system and power plant, leading to the highest harmonic voltage distortion at the point of interconnection. At the end, it compares incremental harmonic voltage distortion level caused by connecting the renewable power plant to the transmission to the allocated harmonic distortion level specified by the utility for each harmonic order. Input data and results are in the same Excel file. The first spreadsheet contains power system impedance low key corner point at the point of interconnection for each harmonic order. So we do not consider just one grid impedance for each harmonic order, but an Rx impedance graph. In the second Excel spreadsheet, we found the harmonic limits defined by the grid code. When the harmonic grid code calculation is completed, the reporting tool populates the following spreadsheets. This summary table indicates the maximum harmonic voltage distortion and the compliance with the grid code. In the next spreadsheet, we see the impedance low key. In blue, it's the boundary, so this is the input that I defined in the first tab. The points inside the impedance graph are individual harmonic voltage distortion level, and the color coding is based on the ratio of individual harmonic distortion on allowed harmonic distortion. There is one plot per harmonic order.
we can see the harmonic distortion for order 11 and 13 are higher than the allowed harmonic level. With that, I conclude this presentation. I will be glad to answer to any questions that you may have. Thank you.